You may have heard that space is empty, but light is a wave, and light can wave out in space. There must be something out there which is waving. In past videos, we have proven the existence of the ether, a medium that carries the actions of electricity and magnetism, carries matter waves, and is the underlying cause of gravitation. In this video, I dispelled the common misconception that the Michelson-Morley experiment disproved the ether. Now, Inductica is moving on to the next step. How do we discover the nature of this medium and gain power over it? The Aharonov-Bohm Effect, electromagnetic potentials, and the principle of locality reveal a possible path forward. Let's understand a hypothesis that drastically simplifies electromagnetism and might explain the nature of the ether here on Inductica. I'll first explain the Aharonov-Bohm effect and a key thing it teaches us about the electromagnetic field. Imagine an experiment where you shoot an electron beam, split it into two beams, and direct it in both directions around a solenoid. When the electron beams overlap and hit a screen together, they form a pattern like this. This is because electrons have some kind of wave-like nature. They actually cancel and add up to one another, just like a wave does. Now here's where it gets really interesting. If you turn the current on in this solenoid, it will change the way that the electrons interfere with one another. The reason for this is because it will cause a phase shift in each beam. The waves on one side of the solenoid will get shifted forward, and the waves on the other side of the solenoid will get shifted backwards. As a result, they will cancel and add to one another differently once you turn on the solenoid and they hit the screen. Now, here's the crazy part. This effect is obviously caused by the current in the solenoid, but if you make the solenoid long enough, the magnetic field out here in the region where the electron is flying is basically zero. The magnetic field is only on the inside of the solenoid. Now, they've run this experiment in a lab with a very long solenoid, one that's so long that the magnetic field is basically zero out here where the electrons are, but the beam is still observed to be affected. The pattern on the screen still changes. Now, how could that possibly be the case when there's no electric or magnetic field along the path of the electrons? Well, it turns out that Aharonov and Bohm explained this effect not with electric and magnetic fields, E and B, but with electromagnetic potentials, A and phi. This is an entirely different but still valid way of predicting electromagnetic effects. Let's go into it. If you conceptualize this experiment in terms of A and phi, you find that there is actually a swirling A field outside the solenoid, even though the B field is zero out there. And in fact, you can calculate the exact phase shift of the electron beam by using the A field. Now, if you think about it, this tells us something really exciting. It means that A and phi give us information about the electromagnetic ether that E and B do not. A and phi are therefore superior concepts. They tell us everything about the electromagnetic force that E and B do, but they also allow us to predict phase shifts in these matter waves. Side note, it's also a way more efficient way. All of electromagnetism can now be written in 3 equations instead of 5. The first 2 explaining how charge causes fields, how charges affect the ether. And the third equation explaining how the fields cause forces, or how the ether affects charges. Further, A and phi give rise to a tantalizing hypothesis for how the electromagnetic ether might actually function. A hypothesis where phi is a fluid density and A is a fluid velocity. What I'll describe to you is my own understanding of a hypothesis put forward by Alexander Martins, a plasma physicist who wrote a paper on the parallels between electromagnetism and fluid mechanics. You can access his papers in the description. Now, you might be immediately skeptical of what I'm saying here because of the issue of gauge freedom. Don't worry, I address this at the end, and it's actually a strength of the hypothesis, not a weakness. The postulates of this hypothesis are simple. 1. The ether consists of small cells. 2. Each cell contains more or less of a hypothetical electromagnetic fluid, which can move from cell to cell. 3. Each bit of this fluid presses on its neighbors, producing pressure throughout the fluid. Now, I have to clarify something. When I say fluid, I don't mean it's literally made of matter in its liquid state, liquid or gaseous state, like water or alcohol, it's probably some kind of entirely new substance. I just mean that it flows and that each bit of it exerts pressure on each other bit. And by pressure, I mean it causes it to move around and to change its positions in these particular ways. Now, the way it works in this hypothesis is that charged objects like protons are regions of the ether that have an excess or a glut of this substance, this fluid. Negatively charged objects like electrons are regions of the ether that have a deficiency or a dearth of this substance. Since each bit of the fluid pushes on each other bit of the fluid, a positive charge, a glut, pushes outward on the surroundings, causing a density gradient, which is the same as an electric field. Meanwhile, a negative charge, a dearth, gives way to its surroundings, causing a density gradient that points radially inward. The density is decreasing as we move towards the center. This explains this part of Maxwell's equations if we think of phi as the density of the fluid. We'll talk about that second time derivative later, by the way. This part of the equation says that charge will cause a concavity in the density of the electromagnetic substance. Okay, real quick, what do I mean by concavity? Now, if you remember your first semester of calculus, remember that the second spatial derivative refers to whether a region is concave up or concave down. So when the charge is positive, the equation shows us that there will be a negative concavity, which just means that the density field will be concave down in the charge's vicinity. It's a little confusing. The concave points down even though it's a positive hump, but just remember, concave down, negative. In contrast, if the charge is negative, this equation actually shows us that the density field will be concave up. And these density gradients cause pressure gradients, causing the substance to get pushed into regions with the lower density. This means that positive charges get pushed into the regions of lower density, and negative charges would get pushed into the regions with the higher density. This is a little subtle in this hypothesis, so let me explain how that works exactly. You wouldn't think this is subtle, but it is. If you have a positive charge in the center here, with a density gradient to the right, that is a medium density region to the right and a low density region to the left, then the substance will get pushed into the low density region on the left. This constitutes a force upon the glut, the positive charge, a force that goes to the left. Meanwhile, if you have a negative charge, a dearth, in the same ambient density gradient, the substance will flow from the high density area to the low density area, and that actually constitutes a force upon the dearth to the right, a force on the negative charge to the right. And this is opposite, of course, to what a positive charge would feel in this same scenario. This effect explains the electrostatic force. That's the term in the Lorenz force equation here. It says that a positive charge will be pushed in the direction of decreasing phi, and negative charges are pushed in the directions of increasing phi. The fluid model proposes a cause for this, that gluts are pushed into the low density areas in order to equalize the pressure, and dearths are pushed into the high density areas in order to equalize the pressure. This gives us a natural segue to explaining magnetism and the AB effect. When a positive charge moves to the right, that constitutes rightward movement of the fluid. Similarly, when a negative charge moves to the left, that also constitutes a movement of the fluid to the right. When you get a movement of the substance in one region, it drags the substance nearby. What this means is that when there's electric current, it creates movement of the electromagnetic substance to either side of that current. And this is why, during the AB effect, a counterclockwise current produces an A field, or a fluid velocity, in that same direction. And if you think about it, this integrates perfectly with the nature of the Aharonov-Bohm effect. If electrons are really just a certain kind of wave in the ether, and those waves have a certain phase, an interior waviness to them, then the fluid velocity actually moves the waviness over. Therefore, during the AB effect, electrons going against A would get phase shifted backwards, while electrons going with A would get phase shifted forward, accounting for the difference in interference when those electrons hit the screen. The movement of this electromagnetic fluid also immediately produces an explanation of magnetic forces. If you've ever found it frustrating that the magnetic force is perpendicular to the magnetic field and you haven't been able to understand why, this part of the hypothesis will be very satisfying for you. If you have two wires next to one another with current going the same way, this will cause the A field, or the fluid velocity, to flow super fast between the two wires. And that's because it's being dragged by both wires at the same time. Now, it follows from our postulates that a higher speed of this fluid will produce a lower pressure, as happens in regular fluids, a la the Bernoulli equation. Now, as a result, there's going to be lower pressure between the wires than there are on either side of the wires. And this is because the velocity between the wires is so much greater than the velocity on either side. This is going to cause a pressure gradient which pushes the two currents together, completely in line with observations. Now, I challenge you to pause and ponder, figure this one out. According to this hypothesis I'm giving you, why would two currents going in opposite directions repel? And you're going to see that that's consistent with observations as well. I've now explained this part of the Lorentz force law, the magnetic force. What this equation is basically saying is that there is a force in the direction of the positive gradient of A dot V. V is the velocity of the charge. Now recall that a dot product is always greater when two vectors point in the same direction and smaller when they point less in the same direction. But what the gradient here is saying is that charges get pushed into regions where the substance velocity, A, and the movement of the charge point more in the same direction. If you think about that, it's equivalent to magnetic forces. Now, what I love about this is that it explains the magnetic force without references to confusing cross products or right-hand rules or any of this. I've always found these things extremely difficult to apply and nearly impossible to make sense of in terms of some kind of actual physical cause and effect relationship. Finally, we still have to explain the last part of the force. This is the induction force. My understanding of this force is as follows. If a current begins ramping up in a wire, it will drag A along with it, causing A to accelerate nearby. In order to accelerate the electromagnetic fluid nearby, there will be drag, or an equal and opposite force on the accelerating charges. This produces a force on these charges opposite the direction of the increase in A. This effect is usually called back EMF or self-inductance, and it causes the current to ramp up slower than it otherwise would. So our hypothesis is completely consistent with this effect. Can we build a machine that computes in the same way that a human being thinks? Very soon, Inductica will be starting an exciting new project. My friend and mentor, Ron Pizzaturo, has developed a new AI data structure using the objectivist epistemology, which I think will fundamentally change the paradigm in AI. I will be presenting the basics of this idea in a new series of videos very soon. So hit subscribe and turn on notifications so that you don't miss that series when it comes out. All right, back to physics. So I've shown you how this fluid hypothesis explains almost all aspects of electromagnetism. It explains how a charge produces concavity in the fluid density of the region. That's an electric field. I've also roughly shown you how a current causes a fluid velocity in its region. I'll give you more details on that later, but that's basically the magnetic field. I've accounted for all three forces as well. I've shown you how a gradient in the density produces a pressure gradient, which pushes charge around. That's the electrostatic force. I've shown you how this perspective drastically simplifies the magnetic force, how moving charges drag the fluid along with it, which create low pressure areas, which draw currents in the same direction together and force currents in opposite direction apart in a Bernoulli style force. Finally, I've explained self-inductance, that it happens when charges accelerate and experience drag as they pull the fluid along with it. Now, I'm afraid to say there is a problem with mutual inductance, and we'll get to that in a moment. What about gauge freedom, though? For those of you who have not heard of gauge freedom, there's a huge problem in claiming that A and phi give some kind of actual property of the ether. The problem is that there are many valid ways of defining A and phi, a huge number of options in assigning the values for these two fields, and all of them agree with observations. If you change the field A A like this, so long as you simultaneously change phi in a related way, the equations will always match the observations. So this makes it very hard to claim that A and phi represent actual physical characteristics of the ether, since there are so many different sets of numerical values that are valid, many gauges. However, there's a physical principle we can invoke, which might eliminate all gauges except for one. And that is the principle of locality. Locality is a principle that has proven true in every single physical phenomena thus far. It's the principle that entities can only act upon entities that they are next to. So, like this, my finger obviously cannot act on the mouse until it is next to the mouse. Now, you might be thinking, wait a second, objects act on each other at a distance all the time. What about gravity? What about electric forces? Yeah, these forces do act over a distance, but they do so only through the spreading of fields. When a new charge appears, let's say a hydrogen loses an electron and becomes positive, the change in the field emanates outward at the speed of light. So while it's true that charges push and pull on one another over a distance, they do so only by influencing the ether around it, which then influences the ether around that, and around that, and so on until it reaches the part of the ether that's near the other charge, at which point the ether then acts on that other charge. If you write Maxwell's equations out in most gauges, you get non-local effects on the fields. So for example, if you write Maxwell's equations out in the Coulomb gauge, you'll get this. And if you carefully think about the first equation, it actually implies that if a charge appears somewhere, then it will instantaneously cause a concavity in the phi field around it. Now, it turns out that the Coulomb gauge and the other non-local gauges don't predict any instantaneous forces. That would contradict the observations. But if we want to put forward the hypothesis that A and phi represent real properties of the ether, then we can rule out any gauge that exhibits a non-local dynamics like this. Now, I haven't proven this, but based on my research so far, this non-locality, this instantaneous change at a distance, shows up in all gauges except one. That is the Lorenz gauge. In the Lorenz gauge, changes spread through the ether at a finite speed. Let me show you how that works and how easy the Lorenz gauge makes this to understand. In the Lorenz gauge, the Maxwell equations look like this. Let's explain the local nature of these equations by looking at the second one. Incidentally, I love writing differential equations with the time derivative isolated on the right side of the equation. This form helps us think about the equation in terms of cause and effect. It explains how the current properties at any given location, which is the left side, gives rise to a change in those properties. That's the right side. Anyway, imagine that we have a wire which at first has no current in it. And let's also say that there's no ambient A field from distant sources. Then, let's say that some current begins to flow in the wire. Examining Maxwell's equations, we can see that there's now a current at this location, but there's no concavity of A yet. Remember, del squared means concavity. So that means that A will accelerate at the location of the current. Once some A appears in the region of the current, let's think about what happens at a location next to the wire. If you think about it, the concavity at this location to the side is positive, concave up. Since there's no current out here, that means that A will accelerate at this neighboring location. It'll start to increase. Now, let's consider what's going on here a little further from the wire. The current is still zero, but the concavity is now positive. And Maxwell's equation tells us once again that this means A will accelerate at this location. The fluid flow will increase. What this basically means is that A continues to spread as the current ramps up in this wire. So you can see that this equation actually shows the local nature of these fields, how sources can cause a gradual spreading of the field in the ether, each bit of the ether only ever changing the parts that are next to it. No non-local action. Now, I leave it as an exercise for you to do on your own to understand how the first Maxwell equation in the Lorenz gauge is local and how it explains in detail how the density of the ether is affected over time by each bit of the ether acting on each other bit of the ether one after another. That'll be a fun exercise if you pause and ponder. So the outcome of this argument is the following. If we wish to treat A and phi as real existence, related to real properties of the ether, then we can only choose gauges with a local dynamics. I don't have a proof for this, but based on my current research, the Lorenz gauge is the only gauge where Maxwell's equations explain things in terms of local dynamics. Not only is the Lorenz gauge famous for making Maxwell's equations easy to think about, but I've shown that this version of the equation also gives rise to a clear, local, very physical cause and effect picture of how each bit of the ether acts on neighboring bits of the ether. Now, even more encouragingly, the Lorenz gauge is obtained by requiring this equation to be true. And this equation is an obvious requirement of the fluid hypothesis. To understand this, we're going to have to understand what the divergence of A means. To understand that, let's write the divergence out, but only in 2 dimensions, since we don't need that 3rd dimension for you to get it. Imagine that we have a grid of ether cells like this. A, of course, is the flow of the fluid, so the x derivative of the x component of A is the difference in flow on this side of the ether cell versus this other side. In this picture, the x derivative is positive since, as we take a step to the right, the x component of the A flow field increases. The y derivative of the y component means the same thing, but just in the y direction. Notice that in this picture, the derivative is also positive, since as we take a step in the y direction, the A flow field in that y direction also increases. If the sum of these 2 derivatives is positive, it means that more fluid is flowing out of the cell than into it. And if it's negative, it means that more fluid is flowing into it than out of it. Now look back at the Lorenz condition. If the divergence is negative, remember more inflow, then the density, according to this equation, has to increase at that location over time. Well, duh, that makes perfect sense. Fluid is flowing into it. Similarly, if the divergence is positive, then it means fluid is flowing out of it, and the density decreases with time. The time derivative here will have to be negative. So not only is the Lorenz gauge mathematically convenient, not only does it have a local dynamics, but it also automatically builds in an obvious aspect of fluid mechanics. So this hypothesis is probably looking pretty good, but I got some bad news. There's currently one aspect of the observation which seems to completely contradict the fluid hypothesis, at least by my estimation, and that's mutual inductance. So let's say you have 2 loops of wire, one beneath the other. Let's say you run a current through the bottom coil. We'll call that the active coil. As the current ramps up in the active coil, it will cause a current in the passive coil above, which goes in the opposite direction. So this is mutual inductance. This is the phenomena, the observation that we're trying to explain. So how would the fluid hypothesis explain this? Well, the active coil would cause A to swirl in the same direction. And this movement of the fluid would be carried upward by the viscous type force that we've already talked about earlier. This will cause an acceleration in the fluid at the location of the passive coil, which will cause the charges in that coil to go against the direction of fluid flow. According to the Lorentz force law written here, and according to experiment, the current in the passive coil above goes opposite the direction of the increase in current in the active coil. This means, once again, that the positive charges experience a force which goes opposite the increase in A. In other words, opposite the direction of fluid acceleration. This does not seem to make any sense. Now, Alexander Martins tells me that this force is completely consistent with the fluid hypothesis, and his paper, which is linked in the description, also says the same, but I've been unable to understand how. I'm really hoping I'm just missing something. Hopefully I can bring him on the program later, and he can convince me. Now, if we're somehow able to make this frickin' inductance term to make sense, we have a very promising hypothesis. Let me summarize. 1. The fact that A and phi can predict the Aharonov-Bohm effect and electric and magnetic fields cannot shows us that A and phi teach us things about the ether that E and B do not. Number 2, we can formulate a hypothesis where there is an electromagnetic fluid which moves through the ether, and each bit of this fluid pushes out on each other bit of this fluid. 3, positive charges under this hypothesis would be gluts in the fluid, and negative charges would be dearths in the fluid. 4. Pressure gradients caused by density gradients cause electrostatic forces. 5. Positive charges are pushed towards the lower pressure areas, and negative charges are pushed towards the higher pressure areas. 6. Currents drag the fluid along with them. 7. Since electrons are themselves waves in the fluid, a movement in this fluid will cause a phase shift in them, or it will move their waviness over. 8. Pressure gradients caused by Bernoulli effects constitute magnetic forces. 9. Further, we can overcome the objection that gauge freedom prevents us from treating A and phi as real fields. If A and phi are to be real properties of the ether, they both must be local. And as far as I've been able to tell, only the Lorenz gauge has a fully local dynamics. Further, they give us this beautiful causal picture of how charges and currents produce changes in the surrounding ether at a finite speed. Number 10. Finally, enforcing the Lorenz gauge requires that we accept this equation, which is completely consistent with the fluid hypothesis. It's just the statement that the density will get smaller over time if the fluid is flowing out of a location, and it will get greater over time if the fluid is flowing into that location. Right now, at least, this has some challenges. I can't see how this works. If the fluid hypothesis is correct, then why the heck is it that positive charges are pushed opposite the direction of the acceleration of the fluid? It doesn't seem to work. I hope this fluid hypothesis of electromagnetism has excited you as much as it has excited me. As I've shown, it has its problems, but even if it's false, this idea serves as an example to us of what kinds of physical cause and effect relationships we should be looking for as we probe deeper into the hidden nature of the electromagnetic field. We do not have to be content juggling mathematical abstractions anymore. We can make hypotheses about the true nature of these cause and effect relationships underneath those abstractions. And with further effort, and with further observations and inferences, we can identify the nature of the ether. That is the path that lies ahead. If you'd like to support our journey down that path, you can donate at patreon.com/Inductica. Supporters will enjoy donor-exclusive lectures. Don't forget to subscribe and to join us on our quest to conquer the ether as this inductive journey continues.